This is a lesson on modeling and regression with radical functions in a precalculus course. In a previous lesson, many previous lessons, I've talked about modeling with functions. I remind you that words mean things and to look for key words or phrases that have mathematical implications. I have been definitely pushing you to develop this sort of like, I need to create an algebraic equation. It's not enough to look at a graph. It's not enough to kind of guess what the answer is. I need to create an equation that I can do algebra on in order to calculate values. Use function notation, use meaningful variables, and always verify your algebraic solution with a graph. Definitely get that graph out. When we're working, that's true for all functions. When we're working with radical functions, what I need to tell you is what forms to assume for the model. So these are the models that I think are useful here. A lot of times, if you just have like a simple radical relationship, you can just use the power of x, right? Whatever rational exponent that is, 1/2, 1/3, whatever that is, right? Whatever radical that is, and then just assume that there's a constant out front. That's the easiest way to do that. That's a lot of times what I do as a physicist, is just use a simple one. It may be that you know more about your model. You may know if there's a shift, if there's some initial x value that you need to consider, or some initial y value that you need to consider with those b's and c's terms. Otherwise, we're just going to assume that there's a scaling factor. I picked out an example of just modeling with radical functions that I see students have struggle with. It's two friends driving off in different directions, and it wants an equation for distance after t hours. So I think students get confused here. What they're looking for is a function of distance in terms of time. We want distance in terms of time. So there's some sort of total distance between these two friends as they travel through time. So we know that distance will be some function of time. I'm going to read the rest of the problem here and get a picture going. I think a picture is good on this one. One friend heads north at 50 miles per hour while the other heads east at 35 miles per hour for the distance between the friends after t hours. So let's take this direction into account. I have one friend heading north, and that friend goes a distance in the northward direction. I have the other friend heading east, and they're not going as fast, so they won't go as far, right? So that will be the distance in the eastward direction. And when I look at the distance between them, when they get so far apart after a distance or after a time period, right? That's going to be their d total, is the hypotenuse of that right triangle. Do you all see a right triangle there? There's a hypotenuse of a right triangle. So I can bring up the Pythagorean here. Pythagorean, a squared plus b squared equals c squared. That's my general equation form, but what I'm going to note is that the total distance here, d total, equals the square root of distance north squared plus distance east squared. That's how I can do that, right? Let's look at another thing. These distances have to relate to the velocities and the time. And you may already know this in your head. You're going to have to use distance equals velocity times time. So the distance north traveled is going to be 50t, and the distance east traveled is 35t. So I'm going to plug these in here, and then I'll have distance as a function of time. The square root of 50t, quantity squared, I have to square both those terms, plus 35t quantity squared. You could be done with that, but I think I'm going to do some factoring overall. Overall, this is 50 squared t squared plus 35 squared t squared. You can see I can factor out a t in both of those terms, right? So that would give me, if I do this, I'm going to just get rid of this t squared and put some parentheses in here. 50 squared plus 35 squared t squared, because t squared is in both those terms. And t squared is under that radical even. So I can bring it out and have t the square root of 50 squared plus 35 squared. You can simplify that however you want. They want an exact answer, I think, for this problem. I'm not 100% certain. And then that way we won't have to decide where to round anything. So this is what I'm going to do is I'm going to note that 50 is 5 squared times 2, right? 25 times 2, and we're squaring that. And then 35 is 5 times 7, and we're squaring that. And it's going to let me bring out a factor of 5 squared. Do you see the factor of 5 squared in both those terms? Plus 7 squared. This is just a 7 squared. All right. If you're not following me all the way on that, I'm not too concerned. But that's how I did it. I didn't get a calculator out at all in order to do this problem. Because I have a 5 squared under the radical, I can bring it out. So I'm going to get 5t, the square root of some constants in here. I get 10 squared plus 7 squared, which is, this 5, there's a whole bracket in here too. I forgot to put those in there. 10 squared plus 49 is 149. And so that's what they want for this answer. The total distance, the distance as a function of time, is 5t, the square root of 149. That's our answer. It's not a radical function, but definitely our strategy included setting up a radical function, right? So hopefully that helps you with that problem, kind of move through, I think, more with the setting up the equation rather than moving through the algebra of it. The last thing I wanted to talk with you on this lecture is just quickly regression with models in general. We're going to do the same thing with radical functions as we've been doing with all other toolkit functions. First thing we always want to do is graph our data, and we're going to note, is it curvy? Does it peak? What happens? I would say this data could be modeled by a line, but there's definitely a nice smooth curve going on. If there's a smoothish curve going on, and what you're going to note for every distance this way, we're not getting as much of an increase in the output. As we increase the input consistently, there's not as much. So there's not a constant slope. That's why I'm going to call this nonlinear, not a constant slope if we put a line in there. We don't have a constant rate of change, average rate of change between those dots. If that was true, if it looked approximately more linear, right, then I would say it's linear, but there's some change going on here. I think knowing a priori that you have a radical function going on is going to be more powerful. And that's true more when you're working with data. You may have data that you expect a radical function to fit well based on other experiments or knowledge about the function in the field of context. So you'll see with my example here, simple harmonic motion can be modeled with a radical function. Last thing here, real quick, report your regression results in proper function notation. Make sure you make note of the meaningful variables that are being used in your function. And the other thing is the correlation coefficient. You need to state how well that data fit the model. The closer to 1 your R squared is, the better. So I went through some physics lessons, some data that I collected with my students in the winter of 2025. In an engineering physics class, we looked at a small mass on a long stream, which is simple harmonic motion. That's what this is. SHM is simple harmonic motion. The model for simple harmonic motion for a small mass on a long string. So if you think about a grandfather clock, you just let a small mass on some long string go back and forth and back and forth. And as long as you're within the small angle, so less than 13 degrees, 10 degrees is what I call it, a really small angle, you're going to get a nice model like this. The period t, all right, big T for time, right? That's what we call period t, as a function of L is given by 2 pi the square root of L over G. And notice that L is our independent variable. It's under a radical, which we expect. I might write this way so that I'll isolate my constant separate from my variable and don't get too upset that I leave the square root of g down in the denominator. I know it's weird to have g in there and then have it in a square root in the denominator. I'm just going to leave it there. It's a number. Take the square root of 9.8. And then those are our constants, and then root L is our variable sort of expression, right? This is our input variable, and then we have some constant out front. So hopefully you're seeing the model that I have set up where I have the period be some constant times L, and I'm going to say to the 1/2 power, okay? And when you take this data, this is real data by a group that I taught. They created this data in lab, so hopefully they took really good data. There's technique when you're collecting data. You need to be very precise to get very good data, right? It says create a regression equation for the data to determine the quality of data collection by calculating a % difference for the value of gravity. Notice the value of gravity is in this constant. So if we get a regression model with some constant and then set it equal to that, we can get like our experimental value of gravity and be able to compare it to the actual, right, our predicted or our actual value of gravity. So that's what we're gonna do. And it also says part C, this isn't part B, part C, to predict the length needed to result in a period of 1 minute. So we want t to equal 1 minute, which I'm right away going to say is 60 seconds. My data is given in seconds, so I'm just going to convert it to seconds. So I did this calculation, this regression in Excel first. That's the first place I did this regression. And it was a fine regression. This is how I had my students do the regression. All right, when I looked at the data, it was kind of curvy. That was the data we had on this slide. It was kind of curvy. It's kind of curvy, and I already knew it was modeled by a radical. All right, and you can see in here what Excel does is it does a power. You select the power regression. This is a power regression, and it optimizes both of these constants. It optimizes this exponent and it optimizes the constant out front, which is fantastic because you can get an awesome model. Do you see it's almost 100% accurate on this data, which is kind of cool. I think that's great for the students that they were able to consistently get results. That's what this tells me, that they consistently got results. We're not saying whether those results were accurate. We can say that the results were consistent, okay? And what I don't like about this model, I love that it's optimized in all sorts of ways, but what I don't like about this model is that we expect this to be the square root of L, which is L to the 1/2 power, right? That's why I said earlier, to the 1/2 power. And instead of getting 0.5, we're getting 0.4654. Interesting enough, but that's not exact. What Desmos does. So let's bring out what Desmos did. And so let me bring this to the front. I like the Desmos equation that was generated. I'm going to get rid of this stuff here so that it doesn't pop up and haunt me. Here's the Desmos result. And we can see the equation here. I forced it to have an exponent of 1/2. Do you all see that? I forced it to have an exponent of 1/2. So when it calculated this value, it gives me the function, and I'm going to write it in proper notation, the function in proper notation. The period as a function of L is going to be 2.07312, the square root of L, exactly. I'm going to note here that this regression returned by Desmos was not as accurate. It says 0.9951, but what I'm going to tell you folks is the original was 0.999. This is 0.9951. I'm okay forcing it to have an exponent of 1/2 with that little bit of loss of accuracy with the model, which tells me not only were the students consistent in collecting their data, but they were accurate as well. They were pretty accurate. So how accurate were they? I think that's a good question. Here's our regression model. That's our first part here. I guess it's part A. I have my letters wrong here. This is part A, regression. Create a regression for the data. There's the regression. Part B, determine the quality. So part B has us say that whatever that constant is in our regression model, that's going to be equal to the stuff that I'm putting in the red box. All of this stuff that I mentioned earlier that is a constant value. So what we're going to say that constant is 2.07312. That has to equal 2 pi divided by the square root of g. So if I solve for g in here, g equals 2 pi divided by 2.07312. And then to isolate g, I have to square it in order to get rid of the square root. And when I calculate this, I get 9.186. And this is a value for g. This is my experimental value for g is what I got. Which isn't terrible. Like I said, that the students were pretty accurate. I knew they were pretty accurate by the model having r squared of 0.9951 when I forced that half up there. Let's calculate a percent difference. A percent difference, in order to calculate percent difference, we're going to take the absolute value of the experimental minus the predicted, and then divide by the predicted, and then multiply by 100. Your teacher may not have you do the absolute value. I don't care if it's, we can look at this and already see it's below the value that we expect. So I know there's a negative sign. So what? I want to know how far off is it, not whether it's below or above. So I'm going to take the experimental 9.186, subtract off the predicted. Our predicted value for gravity, if you don't know, is 9.81. If you have seen the value of gravity in meters per second squared before, it's 9.81. And when we calculate the percent difference here, the percent difference for these students turned out to be 6.36%, which is fantastic for undergraduate students in introductory physics. If it's less than 10%, I am happy. That's a pretty good bench skill development activity, is to have them practice taking good numbers and making good measurements. That's developing bench skills. Let's answer the last part here, part C. You all see the part C down here. Let's get that going. I'll put it in purple fuchsia in the middle. It says, what is the length needed to result in a period of 1 minute? So we're going to say 60 equals 2.07312. The square root of L. We're solving for L. I'm going to get 60 over 2.07312, and then I'm going to square it. And when we calculate this L, it's 837 point something, 837.63 meters, which is actually pretty long. That's a really long length.